In the previous video, we talked about the various coordinate systems that are used to study blade dynamics as well as blade aerodynamics. So now we start looking a little bit more closely at the blade flapping dynamics. How does it flap up and down? And how does this flapping up and down translates into a rotation of the rotor disc, or change in the alpha tip path plane angle, or the rotation of the thrust vector, so that the thrust is pointing in the direction we want to go, providing not only the lift vertically up, but also the propulsive force. So we are going to study those things in this particular module, or in this particular video. So let's take a look at what does the hub look like. So the green line is the shaft. It's coming from the engine. It's rotating and then it's going straight away and is connected to the blades. So the entire rotor is spinning about it. Okay. Now these rods are the control rods. They can move vertically up or down based on the pilot command. Either a human pilot, usually there will be a hydraulic actuator so that pilot does not have to expend a lot of energy, or it may be an autopilot, some kind of a computer control. So regardless, these rods will go up or down. So when they go up, this blue stationary disc that is attached to the fuselage, this blue disc does not rotate. It'll stay put, but it'll tilt either up and down or laterally, sideways, to the pilot's left or to the pilot's right. And these are the ball bearings. And then this is the rotating swash plate. Swash plate is rotating. This one is rotating with the rotor. So this will also tilt up or down. So pilot inputs control input here. So that drives these rods up or down. So that tilts this blue disc up or down. That means front up, behind the pilot back, or to the pilot's left, down, to the right, up, whichever way. You could have any way you want to tilt this disc, you can tilt it. Then the red is going to follow that motion. So when the red disc moves, tilts, these rods going to start going up and down. So when they start going up and down, because they are connected to the blades, they're going to rotate this joint here, causing the blades to pitch up or down. So this is how the pilot's control input results in a blade pitching rotation. It could be collective pitch. That means all the blades have the same rotation. That's what happened in hover. Every blade had the same theta or theta naught. We didn't have to do anything different. Or it could be cyclic pitch, where each blade not only has got a fixed part theta naught, but it also has got a sinusoidally varying pitch control. So all we have to do is push this rod up and put this rod down. That means tilt this blue disc. Then whenever it comes here, this blade will pitch up. This blade here will pitch down. So you see the 180 degrees apart, things are changing. Same way, when this rod goes up, this blade will pitch up, this rod will go down, this blade will pitch down. So you could pitch it up and down. This is a simplistic picture. Another way of looking at it is, this is the pitch control rod, which I have shown here. This is this yellow looking rod here. And it's moving up or down. Then it rotates the blade up or down. So this is in front of the pilot. So when the pilot tilts the swash plate up, in front of the pilot, this disc is going up. But it's not the blade right in front of the pilot that pitches up. Rather, the blade that is to the pilot's side is pitches up. So there's a 90-degree difference between where action is applied and where the actual rotation takes place. So we are applying action here, but the rotation is taking place here. All right. So this is, by the way, is called the feathering axis. This is the shaft axis. And this is called the pitch horn, HORN. This is called the pitch link. Remember, the blades are producing tremendous aerodynamic forces and moments. So if the blade is producing a large nose-down pitching moment, say due to dynamic stall, then it's going to compress this rod. Remember, dynamic stall is not a steady phenomena. It goes in and out. The blade stalls on one side of the rotor disc, then attaches on the other side of the rotor disc. So this nose-down pitching moment will come and go once per rep. So this rod is going to get crushed, compressed, stretched, compressed, stretched. So it'll go through some fatigue cycle. So eventually this rod will crack, break, fail. So they need to be inspected. Pitch links have to be inspected. You may wonder, why don't we make it thicker, bigger, so that they don't break so easily? The problem is they are very heavy, so they will add to the weight. More importantly, remember, this is a circular cylinder cross-section. One CD of a cylinder is 1, whereas a CD of an aerofoil is 0.01. So these are very, very draggy devices that are exposed to the oncoming air. So you don't want to make them very, very thick, because they are going to produce a lot of drag. Indeed, this hub drag is almost as much as the rest of the helicopter drag. So it's a very, very draggy part of it. So people try to cover it up from exposed air. All kind of ways are being looked at to reduce the hub drag. This is an active area of research as well as development. So in a fully articulated rotor, the blade has got a flapping hinge so that it can flap up and down. That relieves the dynamic excess lift on the advancing side. Because of the high dynamic pressure, then the blade will flap up. That produces a downward directed wind, reducing the effective angle of attack, as we will see later. It acts like an inflow. So it reduces the angle of attack, reducing the lift. On the retreating side, opposite happens. The blade will flap down, producing an upwash, increasing the angle of attack. So that's the flapping hinges job. When the blade is flapping up and down and also rotating, it produces tremendous Coriolis forces in this direction. So this region faces a tremendous force in here. It's almost like if it is like a cantilever. So it produces a bending moment all over here. That can produce excessive stresses in the root region. To relieve it, Sierva said, why don't we add a hinge here, so we allow the blade to freely flap forward and backward in the plane of rotation. So this is called a lead-lag hinge. So flapping hinge, lead-lag hinge. This is the pitch bearing, which allows the blade to freely rotate up and down without any friction. So this rod is connected to this outer shell, but with some ball bearings so that there's no friction. This is the pitch control rod we saw, that yellow rod. This is the pitch horn that we saw in the previous picture. Pitch horn, pitch control rod. This is the blade itself. Okay. All right. So this is called a fully articulated rotor. Now, in some tail rotors, rather than having a two separate hinge, one for flapping, which is pointing this way, the other one is pointing vertically, they will combine the two into a single hinge that makes an angle equal to delta 3 as shown in here. This is very common arrangement in tail rotor. You should think of this hinge as the line about which the blade is rotating. Okay? So since this hinge is in delta 3, that rotation therefore takes place about two axes. One is this axis, which is the flapping axis. And it also takes place about this axis, which is the pitch axis. So the tail rotor therefore will both flap and also pitch because of the flap hinge. Because of the way this is connected, let's say that this rotating in this direction, clockwise rotation, if you think of it as a screwdriver, this angular velocity vector is pointing forward, then this is pointing forward. When this is pointing forward, what would happen is the blade will flap down, because again a screwdriver is advancing from right to left. Okay. How about this one? this vector is pointing this way. So if this screwdriver is pointing this way, it's turning, so the blade is going to pitch up. So when the blade flaps down, the blade will pitch up, increasing the lift, causing the blade to flap up. So the tail rotor gets stabilized by this delta 3. So think about it. So let's say that the blade flaps down. That means it's producing a rotation about this axis, which is really a rotation about this axis. So if that rotation is like a screwdriver turning the screw so that the screw is advancing in this direction, then the screw is advancing in this direction. So this component will be going this way. So when the blade is flapping down, losing lift, the pitch will automatically increase, increasing the lift. So this stabilizes the tail rotor. So this angle delta 3 is very important. By increasing the delta 3, you could control the relationship between the flapping dynamics and pitching dynamics of the blade. Usually delta 3 is set to roughly 45 degrees, so that when you pitch the blade, it will flap the blade and vice versa. By the way, tail rotor would also have a pitch horn. So when you move this rod up, that'll pitch the blade, but it'll also cause this line to go up. It'll produce a rotation about this flap hinge, causing the blade to flap. So a single control will cause the blade to flap as well as the pitch. Okay, this is common in tail rotor. In the main rotor, this is a fully articulated rotor. This has got lots of moving parts. Remember, each one is a hinge, like your door hinge. You don't want to have a lot of friction. You don't want to get dirt get in there. You are operating in the sandstorm, Operation Desert Storm. So there's a lot of inspection to be cleaning this, lubricating it. Each one of these hinges, each one of these bearings needs to be inspected. So there's a lot of maintenance there. So they say that in a military scenario, like in Operation Desert Storm, for every hour of flight, you are spending 3 hours maintaining it. Just like my car, for every hour I drive, it spends 3 hours in an auto shop. So people have gone to getting rid of all these hinges, so-called the hingeless rotor. So they have replaced this entire thing with a flexible beam called a flex beam, that like a little bit like a rubber, like an eraser. So it can flap up and down, just like a rubber can be bent up and down, or flap back and forth. So we use a hingeless rotor is what they call it. It will still have a bearing, so a bearing needs to be inspected, this pitch link needs to be inspected, and so forth. Then the next generation will be a hingeless, bearingless rotor, where all these joints are replaced by a deforming Schwarz plate. So Schwarz plate itself deforms under pilot input, so causing the blades to pitch up and down, and the blade is flapping and moving lead lag using the what we call the hingeless, in this case hingeless connector here. Okay. So this is being done in many things, hingeless rotor. So they have a very elastic bending rubber-like connector that connects the shaft to the rotor, free of any hinges. It gets rid of all the maintenance. But this region does see a lot of stresses, so stress fatigue, stress failure of that connector is of a concern also. Here are some more pictures of the lead lag motion. Lead lag motion, by the way, can go out of control, because there's really not a lot of damping. The only resistive force you have is drag. As you know, the drag is very, very small. So sometimes you add an artificial shock absorber like structure, which kind of damps down this lead lag motion. Otherwise, this blade can move too far and hit the blade in front of it, for example. Okay. So you'll have a lead lag hinge plus lead lag damper. Remember, damper is filled with liquid, maybe with a spring like in your car, shock absorber. Then those need to be maintained, they need to be replaced. It's a lot of work. So now we have seen that the blade is usually hinged near the root. It allows it to be flapping up, and also lead lag motion can occur. So aerodynamic forces will cause the blade to move. Centrifugal forces will also cause the blades to move. Now, because everything is unsteady, we are also generating inertial forces, which is m times x double dot, which is the inertial force. Okay. So in forward flight, an equilibrium will be achieved where the net moments at the flapping hinge due to all these forces and the moment generated by the aerodynamic forces, centrifugal forces, and the inertial forces all add up to zero. Sounds complicated? So we are going to show it in a video. We are going to show in the following slides how this happens. Let's take a break here. We will continue in the next video so that this video does not get very